Okay, hi. So, last time I was actually talking about polar coordinates and Cartesian coordinates that we require to actually study how particles or different systems behave in physics. So, we're just setting up the ground or the tools that we will use to actually understand and analyze the world around us. Okay, so first we're actually talking about Cartesian system, which is fairly simple. You have three mutually perpendicular axes, and you have a vector uh, given at in space. Um, so it is time independent. That means there is no time dependence. So you have uh, this vector A, which has three components, and you have the magnitude of the vector given by the square root x squared plus y squared plus z squared. So the sum of the square of the sum the three components rooted, and you have the velocity, which is fairly simple to calculate, and this Cartesian system is used anywhere. So everywhere, to describe planetary motion, anything, right? So you also have like a motion of a car, or all sorts of stuff you can describe. But in some cases, symmetry poses a problem. Not a problem per se. Actually, you can use it to our advantage, such as in electrostatics and so on, as you might have already seen. In that, we use polar coordinates, and we will move on further today to spherical polar and cylindrical polar coordinates. So before that, actually, I have to mention the existence of something called a field in general. So field is again an abstract quantity in space, and I won't go into further detail what exactly a field is, but at this point, we can define something called a scalar field, and obviously there is also something called a vector field. So this a scalar field. So if every point in space, right, is determined by three coordinates, say three coordinates, and then that you can associate a scalar function phi, and this scalar function can be of any form. It can be like this. It can be also like this. So anything, and it will represent any scalar, any function that is a scalar. Right? It could be temperature, it could be luminosity, it could be intensity, it could be almost anything, right? So it can. So and further, and we will also do some further analysis on scalar fields, such as bringing in quantities such as divergence, gradient, uh, Laplacian, and so on. But for now, we'll just define something called a scalar field, which is just used to represent any scalar function or a number associated in space xyz. So it can be temperature, luminosity, intensity, anything for that matter of fact. But anyways, so now let's move on to polar coordinates. So we already saw that polar coordinates are also described by two variables, r cap and theta cap, which are mutually orthogonal to each other, and they're represented by so r vector is represented by r cos theta I cap plus r sin theta j cap, and since they're orthogonal, right, the dot product should be 0. So orthogonal, so if I must say if two vectors are orthogonal, the dot product is 0 because cos pi by 2 is 0. So it's just you just have to do dot product. That's it. So that's why we define. So you can actually dot r and theta cap. So I've written it here, r cap, theta cap, to find that they are they will give 0. So we already saw velocity r dot r cap plus r theta dot theta cap by just differentiating this infinitesimal vector dr. So again, just a revision. Dr has two components. Your radial component. So this is often. So I forgot to mention in the previous video that this is the radial component, and this is your transverse component. So yeah, so we will move further. So now we can try to find acceleration. You can pause the video and try to find it. It's a useful exercise. So acceleration is just dv by dt, which is and this is the first order time derivative. So dot means first order and double dot means second order. And so we have to use chain rule. As in chain, I mean chain, not chain rule, product rule. So keeping this constant. So now we can see that we have time derivatives in unit vectors as well. So that is why I've calculated these two quantities here. We have time derivatives in unit vectors as well. So that is why we have to calculate the time derivative of unit vectors in polar coordinates. So that is why I've calculated them before. So we are going to group. So again, we can substitute r cap dot as r dot theta cap plus r theta plus minus r dot theta dot square r cap. So grouping all the terms, we get grouping all the r cap terms, you get r double dot minus r dot theta dot square r cap plus r theta double dot plus 2 r dot theta dot theta cap. So this is your acceleration in polar coordinates, which is fairly straightforward derivation. And we will be, again, this is the radial component and that is the transverse component. So usually, I'm just giving a further example. If we were talking about planetary motion, as we will, I will talk about it later. So for example, if a planet is moving in an ellipse, or I mean for any example, any circular or whatever, right? On Earth you can say, and this is the sun at the center, this is the Earth in a fairly circular orbit, its angular momentum is conserved. So angular momentum is a conserved quantity, and due to that, the transverse component will go away. So the acceleration of our planet will only have the radial component. So there's a, again, you can show it, but for this lecture, for that matter of fact, I will not go into further detail, but these are some of the applications that are there. Okay, so now we can actually move on further into, so again, this is a two-dimensional coordinate system, and usually we are made to deal with 3 dimensions. So before going on further, I would like to generalize spherical polar coordinates, I mean the coordinate systems in general. So they come under something called curvilinear coordinates. So again, curvilinear, so I am generalizing it, and so far we have, again, polar coordinates and Cartesian coordinates is a special case of curvilinear coordinates, because the coordinate surfaces or the axes intersect at right angles. So that's why they are called orthogonal curvilinear coordinates. So this is a special case of curvilinear coordinates. But in general, it is good to generalize curvilinear coordinates in general. So, okay. So, the first thing is your spherical polar system. So again, as the name suggests, this is also a special case of orthogonal coordinate systems. Again, We start with 3 axes. But in this case, our coordinates are going to be in a sphere. So, first of all, you have a point in space. So, what does a sphere have? So, before going further, we have to see how you can move in a sphere, right? The lack of better three-dimensional drawings. It's very bad, but I have to bear with it. So, you have a sphere. So, how can you move in a sphere? Well, you can move like this. You can move radially. So as you move radially outward, the sphere gets bigger and bigger and bigger. The radius increases. You can move like this, and you can move like this, vertically. So you can move along the equator, you can move along the poles. You can see. So it's just like a ball, right? How can you move if you're on the surface of the ball? How can you move? So you can jump. That means the radius will increase. You can move like this along the equator, and you can move so you can move latitudinally and longitudinally. Okay, so now, so describe it. Mathematically describing it is not hard, but it needs some work. So you have a radius, your point P denoted by r, theta and phi. So these are equal, so that it's no more x, y, z anymore. So this accounts for the fact that motion can be angular. Motion can be longitudinal, latitudinal, and also radial. So that is what will form a sphere. That is what is going to form a sphere. So r is basically the outward radial vector. Phi is going to be you can say your latitudinal angle. So that means it is going to describe how it rotates horizontally, and theta is going to be how it rotates vertically. So you can describe it. Okay. So this is going to be your r cap vector. So theta cap is going to be orthogonal to r cap. So this is going to be a theta cap vector. Okay. So you can actually draw projection. So the phi cap is actually going to be a projection of your r vector. So see projection. So this is going to be a phi, angle phi. So it accounts for the motion in horizontal way. So the ball will move like this, horizontal. Then, so this is, so we can extend the axis like this. Maybe, yeah. So this will form kind of like a sphere, right? So this is the part of a sphere. This is just the part of a sphere. So imagine this is this is a very bad point, but imagine this is the earth. This is just part of a sphere. So the earth is actually opened up. So you have earth like this. So imagine you open up earth and you see what is going on inside. So that is what is happening. Okay, so we have a crude diagram here, and yeah, this is theta. So it accounts for the vertical motion. So we have to express our coordinates in terms of r, theta and phi, in terms of x, y, z. So x should be represented in terms of r, theta, phi. Y should be represented by r, theta, phi. Z should be represented by r, theta, phi. That's what we did in polar system as well. So x is, if you want to find this point P represented in these three coordinates. So let's see. So this is r. So r sine theta cos phi. So r sine theta is accounting for, so what is r sine theta? So this is r, so sine theta is perpendicular by hypotenuse, perpendicular by hypotenuse, so this is p. So this is r sine theta, and you're projecting it downwards to account for that other angle, so cos phi. And y will be r sine theta sine phi, because you're moving. So that is, I mean, you can actually take an analogy from polar coordinates, which is r cos theta, y is r sine theta. So similarly, y should be r sine theta sine phi. Z is r cos theta, because it is just accounting for this component. And yes, so you have to define the limits as well. R can go from 0 to infinity. Y accounts for the, sorry, phi accounts for the horizontal motion 0 to 2 pi, because 2 pi is, if you have a circle, you go fully, you go 2 pi radians. Theta accounts for the vertical motion, so from here to here, 0 to pi only accounts for this 0 pi. Okay, so this is your spherical polar coordinates, and it's generally used everywhere in electrostatics, as we will see later on. Okay, next is your cylindrical polar system. So basically, as the name suggests, it's all a cylinder. So again, you have to see how a object can move in a cylinder. So generally, if you have a cylindrical symmetry, as you will see again, like you will see, will deal with Gaussian surfaces and so on. So again, an object, so this is a cylinder. An object can, so this is your x, y, z. So y, x. Okay. So an object can move like this, radially outward. So I can draw it here. So an object can move radially outward. So let us call it r. And it can move along the axis z. So let us call it z. Right? So I will call it z. And it can move around the cylinder as well. It can move around the cylinder as well. See, it can't move vertically, longitudinally, because the curvature of the cylinder only restricts it to move, latitudinally, like this. It cannot move like this because the curvature doesn't allow. I mean, if the cylinder was like this, then yeah, obviously it can move like this. But we have a horizontal cylinder, so that's why the particle can only move along the curvature of the cylinder, the curved surface area. So r z phi, or lateral, so notation r phi z. So this is r cap, z cap, and phi cap. And yeah, so this is, you can say, this is your angle phi. Okay, so always remember, always think about how the particle can move in all these systems. In polar coordinates, it can either move radially outward or around the circle. In spherical polar, it can move in phi direction, latitudinally, longitudinally, and radially outward, because that's how a sphere, just imagine you're on a sphere and how you can move in a sphere. And in cylindrical, you can move radially outward along the curved surface area and along the z-axis, because a cylinder can, so if you think about it, a cylinder can have different lengths along the z-axis, right? You can have this, you can have this length, you can have this length. So similarly, you can also move along the z-axis. So one of your coordinate coordinates, as in your freedom to move, is along the z-axis. So in this case, your x will be r cos phi. If you think about it, so just your x-axis. So sorry, this is your x, y. Right? No, sorry. This is I mean, you can change it, interchange it, but for this problem, x is r cos phi, y is r sin phi, z is just always z. So these are your three coordinates for cylindrical polar system. And again, you can represent uh, velocity and acceleration in all these systems, but the derivation is quite long because you're dealing with three variables here. Over there, you're only dealing with two variables, and itself it was quite a derivation. So you're dealing with three variables, and again, I can define the limits. Zero to infinity. Phi goes from 0 to 2 pi, and z goes from 0 to 1. So yeah, so that is your spherical cylindrical system. And okay, sorry, z goes from minus infinity to infinity, because your cylinder can also extend downwards, right, till infinity, but your radius is fixed at the origin. So the cylinder can only expand about the origin, not so radius. That's why radius only goes from 0, but z can extend downwards as well, so it's minus infinity. So that is just the crux of these systems, but there is further to be done. We have to define volume elements, surface elements, line elements using Jacobian. So that is another quantity that I will be talking about later. But for this lecture, I guess it's fine. Again, you can define your dr vector, your b vector, and your a vector for all these systems. So I will be continuing this from the next time. So thanks.